Right.
On that note, it's time now for us to segue into our next talk, and it is by Dr. Bingsheng. He's currently a Dean's Chair, Associate Professor, and Vice Dean Research at the School of Computing, National University of Singapore. Before that, he was a faculty member in the Nanyang Technological University, Singapore, and held a research position in the System Research Group of Microsoft Research Asia, where his major research was building high-performance cloud computing systems for Microsoft. He got the bachelor degree in Shanghai Jiao Tong University and the PhD degree in Hong Kong University of Science and Technology. His current research interests include cloud computing, database systems, and high-performance computing. He has served in the editor board of international journals, including the IEEE Transactions on Cloud Computing, IEEE Transactions on Parallel and Distributed Systems, IEEE Transactions on Knowledge and Data Engineering, Springer Journal of Distributed and Parallel Databases, and ACM Computing Surveys. He's an ACM Distinguished Member, presenting to you with Parallel Graph Processing Systems on Heterogeneous Architectures, Dr. Bingsheng Ha. Over to you, sir.
Thank you, Anvith. So let me share my screen first.
Sure. You're audible and your video is also visible.
So you can hear me now, right?
Yes, we can hear you and your screen is visible, sir. Over to you.
Okay, great. How everyone? Thanks for Anvis for introduction. So today I will present the large crowd processing on heterogeneous architectures. So as you can see, we will actually talk about systems, applications, and also some architectural implications. This is the joint work with a lot of my students and colleagues in NUS and also UIUC and so on. So this is outline of my presentation. I will first talk about, give you some background about pervasive graph processing, why I choose to research on the system and algorithms of graph processing. And then I will give some motivations, basically why heterogeneous architectures matter. And then I will pick two pieces of our recent work. One is Thunder GP, the other one is talk about how to adjust the parallelism for graph processing. And then I will summarize this talk, and then I will present the future work. First of all, I suppose you already know graph data structures are quite pervasive. As actually is we trying to represent the relationship between different entities in different entities, and then the entities becomes a vertex, and the relationship actually along the edge. As you can see here, this is actually graphs can be in social network, can be in road network, can in bio network, and so on and so on. I would say this data structure is very powerful in representing the relationship between different entities. But actually there are quite some challenges from the graph processing. On the one hand is that you can see graph can be very big, and also size can be very different. As you can see on the left hand side, the US road network is in 100 millions of vertex. But if you look at on our right hand side, it's actually can go up. Brain scale actually is 100 tera vertices. So this is really amazing. We have a very wide spectrum of graph. Okay, but so hold on. One thing is that graph is big, but even make it more challenging is graph is sparse and actually irregular. So when I say sparse, as you can see in this figure I show you, if you learn, is actually the degree of basically number of labels of per vertex. This is really skewed. That means actually some small portion of the vertex has very high degree, right? And then a lot of other vertices, they have very low degree. So that will cause in practice we call power law distribution and so on. So this kind of distribution cause a lot of processing imbalance. If you think about the threads we take, I mean, in computing you're trying to consider load balancing. This kind of distribution can be very challenging for computing system for load balancing. On the other hand, actually can be very, very irregular and also sparse. Then actually we cause the problem in data storage so that we can make efficient access and also reduce the storage size. So you can see actually, as I mentioned, actually it's quite, I present the challenge in volume and variety, but actually there are other challenges we learn from the textbook, the big data challenges. In the other two, often we talk about velocity and convexity. So these two are actually quite common in graph data structure also. For example, velocity is actually graph are changing from now and then. For example, social network, we can see new edges and new vertices are actually being added from now and then. Deletion also can happen. So this is really, we can see these challenges in the graph processing. So you may wonder what are the application for graph. Actually, graph processing is quite powerful. So you can see we actually have some in Singapore. We have an institute, Asian Institute of Digital Finance, AIDF. In that, I'm actually have a project to research how to use graph processing to address the frauds in digital finance. So this actually shows you one thing is about the payment, is about the transaction frauds. So I don't want to go into details, but you can see actually here we can use path analysis to identify some fraud based on some previous frauds evidence or some frauds credit card and so on. Basically, it becomes a path analysis. On the other hand, money laundering can be very important to detect in the banking system. So you can see actually in those very complex source account and destination account, actually there's research that we can formulate this money laundering with a tripartite subgraph. So that actually is another example. And we actually have more. Okay, so basically in merchant, for example, we talk about some online transactions, online marketplace. So this is actually quite often people try to take advantage of the illegally for the promotion, for example, and they create a lot of fake account to do these kind of fake transactions. Typically, we can use a cycle to detect this kind of fraud, this kind of frauds. So as you can see, that's how we actually look at the graph application. There are many more interesting structures. For example, recently we look at the dense structure to identify the potential frauds in a large graph. Okay, so this is on one hand, we have large graph processing. On the other hand, we really care about the performance. As you can see just now, the applications, all those applications face a lot of transactions, and we need to do the fraud detection in real time so that we can catch up with the volume of the online transactions, and we want to detect the frauds earlier so that we can stop them, right? So so that's why when we talk about this, we of course we research on algorithms, but on the other hand, if we look at the hardware side, is that we actually has a lot of interesting observations. So this actually shows you the part in the past few decades how the CPU has developed. So you can see very interestingly is that, oh sorry, let me, okay. Oh. So very interestingly, you can see this is the number of transistors, right? It goes up very linearly. So that means the number of transistor we put into the processor actually grows almost like still very is. So by the way, this is log scale. So actually that means it actually increase dramatically along the years. But if you look at the power, if you look at the frequency, if you look at the single core performance, they have become quite flat. So that's why people say it is end of Moore's law. And it becomes a single core performance can be a problem. So people look at different processor because of this to take advantage of this large amount of transistors. So people talk about GPU, FPGA, and ASIC, even ASIC to talk about to accelerate machine learning and the data processing applications. And why this is important, I give you one example is on GPU, right? As you can see here, actually I showed you the memory bandwidth, and also the computation power of to compare CPU and GPU. The green one, as you can see, actually both of them actually increase, but the GPU actually increase much faster. Okay, so that's why you can see GPUs nowadays has been very standard computing accelerators in cloud and supercomputers and so on. And FPGA, I think, is catching up. You can see actually it becomes more and more FPGA become available in the cloud. For example, Amazon EC2 and Alibaba, they have their FPGA in the public cloud. So this is also because similarly we have seen more logics, is like more cells inside FPGA, so that we can actually put in more complex applications or systems on FPGA. And if you look at the memory and storage, again, we can see the price actually dropped significantly in the past decades. So this is somehow actually, as I mentioned just now, graph processing can be large, and also there are a lot of random access, and then the memory speed is become very important. So that's why we need to, as the price goes down, we can put them in the main memory, for example, and then, but still, the random access can be very costly. So we still need to optimize the locality. So the network is actually improving a lot in the past. So if we look at the price, also on the same hand, the price also drops. So put them all together is that you can access them into cloud very easily. Those hardware are available, so we can easily build build those systems with, as long as you have a credit card, you can get access those advanced hardware. So this is something what we expect, okay, in the next coming 5 to 10 years. So I think we can see the processor have more cores, and we do have some heterogeneous. So we do see some heterogeneous hardware, so FPGA, ASIC, and so on. So I talk about the storage side and also networking side. Put them all together, I think we have more and more powerful hardware, and then that's why but on the other hand, it's also very complex. So we complicated. So actually, in the past, as our research showed, so that if we need to carefully design a system and algorithm so that we can take advantage of those hardware. So if we don't do that, the current algorithm can only utilize maybe just 10% of those hardware power, or even less than 10% sometimes. So this is really interesting and important problem to address. And of course, people talk about the next generation, the heterogeneous architecture. So people talk about quantum computing and so on. So as the time limit, I won't go into details, but I actually point to you actually here is that there's a vision article talk about the computer architecture in the next 15 years by the computer architecture community. Okay, so there are many interesting stuff going forward. So this is the overview of my research. Okay, so on the one hand, you can see we have heterogeneous data source. Okay, we have heterogeneous data source here. So something in the past I have done. So actually I have done in the graph processing for decades. Okay, so we have developed graph processing for single data source, but recently we find that actually graph can be a very powerful data structure to combine different data sources. Okay, for example, some data source from social network, some from online business, some from company, and so on. How we actually combine those data source together to digest, to dig out the value. So this is that's very interesting and very important. Graph is one of the very flexible and powerful data structure for this kind of application. And on the other hand, I introduced to you, we have heterogeneous architecture. So put them all together, we need to have 3 layers of research. One is the infrastructure. We need to come up with, we need to really think about new algorithms, new program models, real one-time system so that we can address the hardware utilization, and particularly for graph processing. And then on top of that, we build data and the graph learning systems. We talk about graph database, graph machine learning systems, and also recently I'm quite interested in federated learning system also. As we can see, there are multiple data source, and maybe they with most of them with privacy concern. But anyway, today I will go focus on graph. So on top of that, we will actually will support different applications like what I just give you, fraud detection, and there are other applications we are interested in also, and also we are doing research on this. So by doing this, this is the architecture we have. So if you look at this from again from bottom up, is that we have the hardware, different hardware, and then we search on different pre-processing, because I mentioned to you the graph processing can be very irregular, it can be very sparse. So how to organize the graph is very important. Sometimes we also need to look at ordering, graph ordering, so that we can, for example, we can order the vertex and edge so that we can have a better locality. And for large graph, we actually see research on how to do the graph partitioning in a timely manner. And then on top of the pre-processing, we do parallel graph processing. So in this research topic, there are a lot of interesting issues. So we look at how we do hardware and software co-design. We see how we actually do architecture-aware accelerations. We actually also look at how to do programming models, no matter it's a vertex-centric, edge-centric, and hybrid, and so on. So this is really something interesting we need to explore there. And then on top of that, we support different applications like BFS, shortest path, PageRank, and also connected component, and so on. So this is something I would say this is really different. Is a research problem with different community working on that. Okay, so that in the past we have done a lot of interesting stuff along the way. So I will skip them. Instead I will give you more detail later. And we actually deploy the graph processing in some application, like this is one application we actually use our graph processing platform to address the low latency scheduling for the auto vehicles scheduling in the Singapore port. So because in the next generation of Singapore port, actually there are thousands to tens of thousands of auto vehicles to deliver the cargoes. So the second one is actually, this is done with Huawei. Okay, so we actually done with the telecom is in Huawei, how to actually recover the fiber, the fiber connections when we need to do the fiber routing again. If there's some failure happen in the fiber, we need to do the recovery very fast. So that's why we use graph processing, GPU-based graph processing to accelerate this kind of recovery. So this is actually, as I mentioned, is collaboration with Huawei in China. So there are other things we have done is like dengue clusters. We have tried to use GNN to predict the COVID-19 cases. So this actually we achieved quite good accuracy. So there is actually a demo in the link, but the color doesn't see. But anyway, you can, if you go to see, I can do it for you. Okay, again, I can give you the link if you are interested. So we also do, as I mentioned, we actually do it in a lot of fraud detections in digital finance with the real application from Alibaba and Grab, and also some other insurance company. So this I will skip that. So there's a demo here if you are interested. So now let me give you some details about our two pieces of work. Given the time, I think I will go through them in slightly more details, but I have to control the time though. So first of all, as I say, why we care about FPGA, right? So because I think FPGA has already been really emerging recently in different data centers, as you can see the examples here. And there are application acceleration here, as you can see, different speed up over the CPU. So this really looks promising. And so that's why we look at how to do graph processing on FPGA. So you may wonder why we do graph processing on FPGA is because, as you can see, or later I will show you, actually graph processing has a lot of fine-grained parallelism. So basically, we will define the processing on vertices and edge. You can see a graph have millions of vertices and edge. So this kind of parallelism is really fine-grained. So this is really fit for FPGA, where you have, compared with CPU, you have really low-level fine-grained parallelism to control. Okay, of course, there are other flexibility of FPGA, like low power consumption, and also the flexibility in with configuration. So all these are how these good features are actually motivate us to look at high performance graph processing on FPGA. But more importantly, actually, we use FPGA as one step forward to look at specific graph accelerator. Okay, so this is something very interesting. We want to look at the design of ASIC accelerators. So when we look at FPGA, we need to choose different programming tools. Traditionally, we choose RTL. So this is really low-level hardware description languages to develop FPGA. But we find that this is really difficult to scale to large graph processing, because we want to support different graph application, right? So this is really, we want to allow the users to define their logics. Ideally, the users should have a transparent programming framework that they focus on their logics. For example, they want to detect their frauds, they want to calculate their shortest path. So that is something users care about. So that's why we come out with some HLLS. So we should, based on high-level programming languages like C or C++, so that people can develop their own applications. Okay, so that's why we choose HLLS. So, and then that's why we developed Thunder GP. Okay, so we actually make it open source. You can in the GitHub you can find that. So so there are many challenges we developed when we developed Thunder GP. So let me give you one example here. So we actually use the gaps model, program model. So basically, you think about page rank. You need to scatter the partial page rank to your neighborhood, and then with those partial ranks, you gather them to try to combine them. So this is apply function. So all this scatter, gather, and apply, you can define your own logic. Okay, you can based on them, you can develop your page rank, shortest path. You can develop whatever application as long as you want to define those three APIs. But the problem is actually we can actually do because of locality, we develop VRAM buffering, and also we care about multiple processing element for parallel processing. So all this looks well, right? But the thing is, the problem is really on the data shuffling part. Remember, we have the thing about that. We have a shuffling, right? So basically, you have you have a scatter, right? So basically, given a destination, you want to output the result to some destiny. So this is, for example, I give you an example here. You have a processing element. So you can think about A cores or A threads, okay? And then you try to output A tuples with the destiny and values in this format to the downstream processing element. So basically, you have two sets. One set is producer, the other is consumer. So the consumer will accept the tuples. So in this case, basically it's a scatter, and the problem is you only know the destination during the runtime. So this is in FPGA it's really a disaster in the sense that you have to pay, because this is really hardware, right? You need to, in FPGA, you need to have the bitstream already connected the so-called connections. So there are some on HRS, again, they elect very fine-grained control logic for this kind of shuffling. So if you look at existing methods, so one method is called polling. You can do basically the consumer will poll every producer element processing at PE so that you know, but you can see this will take 8 cycles for 8 tuples in this example. If you have more PE, then this will take more cycles, right? So this is very, very bad. And the other hand, you can use another approach we call convergency kernel. So actually, again, it takes a lot of II, we have 100 cycles. So all this together, actually, it causes a lot of problems. So now, can we address this approach? Is that we want to resolve this one-time dependence, okay, this kind of conflicts. So one approach in our mind is that, okay, so instead of we do runtime shuffling to do this one by one, why not what if we know the position? So we want to calculate the position to output. So and also we want to know how to know about the position and number of tuples. Okay, so these factors are very important to resolve the conflicts. If we know this information, every PE knows this information, then we can do the scattering in parallel, right? So actually, we come out with a very interesting solution. Think about that. Here is we have only a PE, right? So the number of possibilities scheme, the number of possible the number of possible solutions for output position and number of tuples is only the number is only 2 powered by 8, right? It's only 256 solution here. So that's why we come out with a very compact encoding that we actually will encode this 256 solution. So basically, you can see this is the 256 possible solution, and then each of them consider is a decoder. You can think about it as a hash table in software, but we implement hardware, so it's a decoder to get the number of results and also their positions. Okay, so with this one, each PE we have this piece of information so that every PE can do the scattering in parallel. Okay, so and then so that we can actually do it one cycle for one tuple in parallel. Okay, so that is very is already bandwidth optimal. So we have, as I mentioned, we have API, we have developed system is in the GitHub here. So this something looks like if we want to implement sparse matrix vector multiplication. So in our Sounder GP, so this is something like very high level programming, right? So that is good for users. And so we have evaluated on real FPGA, on real hardware, so with different graph data sets here. So as you can see, our shuffling can be over 100 times better than existing solutions. Okay, and our memory optimization actually is very significant. So this shows you that actually on FPGA we need to optimize the system very carefully so that we can actually deliver a very good performance. So this is compared with the state of the art. By the way, the state of the art will actually use HDL, say they use RTL to implement their code, and R is on high-level programming languages, and also R is a framework. So we can see still we can achieve a speed up better than them. Okay, so from more than 40% faster, or even 2 times faster. Okay, so we have make it open source. Actually, we have by the way, and also this paper is picked as the best papers collections in FPGA 2021. So the next piece of work is how we look at the parallelism. So I will give you one example. As this actually, as I mentioned to you just now, we actually deploy our graph processing algorithms on Huawei's fiber network, and also the next generation of the future pod. So one of the things they are looking at the routing is that they have the constraint shortest path. Basically, is that instead of finding the plain shortest path, there's some constraint. For example, we want to have some bandwidth guarantee on the path. For example, I want to find the shortest path with the bandwidth larger than a threshold. So this kind of shortest path, it actually is usually we use a so-called we have to use a solver to do this. So actually, this is so-called a very standard labeling algorithm. But the problem is in the labeling algorithm is that we need to consider whether we exploit or explore. So we want to take how many labels we want to expand at the same time. So this is we define as the degree of parallelism. So this is something very tricky though. So if we want to expand more, basically you try to have more parallelism, then you have a lot, you may explore a lot of unnecessary labels, right? Because some label can be prone later. So if you do small, you have a small degree of parallelism, then you cannot take advantage of all the processing power. So this is really has a trade-off. So we actually try to balance these two. As you can see, the performance here. So the degree actually is like your concave shape. Okay, everyone is a concave shape. There is a value that is there is some best degree of parallelism there, but the value can be very different among the graph, and also can be very different among the different application also. So that's why we actually developed a system called Wine on GPU, so that we adaptively control the parallelism to balance the hardware utilization and also growth of the labels. Okay, so and also we developed a very effective pruning. So for more detail, you can refer to our paper. So let me present you some results. So first of all, we look at, if we compare with the CPU solution with 40 cores, actually is 2 sockets, and then our one GPU actually can be like 18 times or even 42 times faster than the existing solutions on 2 sockets of CPU. And this is to show you the scalability of our solution. So you can see for the CPU-based solution, you can actually, if you think about the millions of nodes here, so all existing solution, they cannot achieve very good latency. Actually, it's over 10 seconds, right? So this is really slow, and it's hard to say real time for a lot of applications. But for, you can see for our solution in the green rectangle, in the green triangle, so actually it can achieve sub-second latency on this kind of scale of graph. So that actually is demonstrate very low latency, as I mentioned, in the pod application. So if we actually compare with approximate solution, we achieve a similar, we don't have pre-processing time, by the way, and existing approximate solution takes a long time to pre-processing the graph. So if the graph can be dynamic, then the solution becomes impractical, and also they have relative errors there. But in the end, our solution is, again, I'm saying we actually achieve sub-second latency on different graphs. So there are other works we are ongoing. So we are actually trying to do some fraud detections and graph learning, and also some recently we have open source a random walk engine for graph neural network. So I would say this is something very interesting. If we have another chance, I will share with you this exciting result next time. So in summary, so I would say graph processing can be very interesting and very challenging research topic on heterogeneous architecture. And we have so far focused on volume and variety, but I think the other two, velocity and complexity, can be very interesting also. We are looking at these of the other two challenges here. So we have open source our system. If you are interested, you can take a look at them. So again, let's look at some future work. So I would say this is auto graph. Okay, graph, by the way, has graph itself is not a new topic. It has been there for decades. I think even in 1950s, there are some graph theory papers, but I think recently, because of large graph, and we are also facing a lot of interesting applications, we are facing those a few V challenges here. Okay, so there's something interesting we want to see. For example, the first one is how to beat the CPU or GPU. Particularly GPU is very hard to beat at the moment. So for energy efficiency, yes, FPGA can do better than GPU and CPU. But the absolute performance is still not ideal. We are still working on the next generation of FPGA, so that we want to see, for example, the next generation, the latest FPGA has the high bandwidth memory. So we really want to leverage those high bandwidth memory to improve our graph processing. So see whether we can beat GPU or not. And the other hand is that we want to go beyond the simple graphs. We want to look at small complex graph with properties. And lastly, we actually want to go beyond the simple processing model. We want to look at graph neural network and so on. So in the end, it's really interesting, and a lot of application and system are ongoing. And also we ask ourselves, what are the common building blocks in these so many applications? Can we come out with something like SQL for relational database? I think that is something interesting to explore. Okay. So this is our reference. So I think I have to stop here due to time. Okay. Thanks.
Thank you, Ganshe, Herbo. Thank you, Professor He. It was really nice to have you in the session today. Rightly said that the graph processing has been like a pretty old subject, but now a lot of interesting big problems, data analytics problems can all be mapped to graphs. And with the bigger data sets, the latency and the processing definitely is something that we look forward to improving. So you talked about your work on the FPGA. So have you also looked at partial reconfiguration of FPGAs so that if you detect like certain data flows are more important for a certain data set, you could change and adjust to those?
Yeah, that is a very interesting question. So the partial reconfiguration is very, I would say it has been researched on FPGA community for a long time. And there are some architecture paper on this, but in terms of actual implementation on real systems, I think there are still not that many works on that dimension. So recently we actually look at this topic because we actually find that different graph structures, they may prefer different different hardware structures, different hardware architectures. So for example, there are some, I give you an example, okay? There are some vertices in the graph with a high degree. So maybe it actually requires a very complex pipeline, hardware pipeline. And then there are some vertices with small degree. Then we can actually, we can use some simple pipeline to process them. So that comes to your partial reconfiguration, is that if the graph has changed slightly, can we do partial reconfiguration to change some of those pipelines from the large pipeline to small pipelines, or from small pipeline to large pipelines? So that is actually something ongoing. We are doing this piece of work.
Great, great. There are more questions for you, Professor. So, like across the different types of hardware, you compared between the CPU and GPU, but from the audience, there's a question about ARM processor systems. So you get lots of cores on the ARM processors. So is ARM a contender, or does it look promising?
Yeah, so that's also very interesting too. So first of all, I haven't tried it on ARM because actually, we actually quite some time ago I talked with the Singapore Huawei lab. So we need a cluster on ARM, but actually due to the COVID, we haven't really make a deal. Okay, but it's very interesting to look at the graph processing on ARM processors. What I can see on ARM processor, there's some advantage for ARM is that ARM processor tends to have more cores and also more parallelism. So and also the instruction set can be very different to CPU and GPU. So there's some very interesting research to be done on the graph processing. So I don't know which one is faster because I haven't done any research on ARM yet. So, but I see a lot of interesting things there. And also our past experience is that if the things are carefully designed, the hardware utilization can be improved a lot. For example, as you can see on our GPU solution, actually if you can do research on carefully designed algorithms and systems, you can improve a lot. So I think we can see the same things on ARM. So, but in the end, which one is better? I don't know. And also it depends on the memory's subsystem also, right? So I think it's not an easy question to answer. In the end, we need to carefully benchmark them so that we understand the pros and cons of different architectures.
We are running short of time, but we have multiple questions for you. Anwar, do we have time for one more question? Or?
No, I believe we are way out of time, but Professor Bingsheng, if you can answer the questions in the Q&A box, we will be very grateful.
Sure, let me do it.
Yeah.
Sure.
And there are some questions in chat as well, so please do, sir, if you have the time, please do.
Sure. Let me do it.
With that, I would like to
thank you so much.
Thank you.
Thank you so much, Ankit, for driving that session, and thank you, Professor He, for your session and for spending the time with us. With that, ladies and